If you've been studying physics very long, you've probably heard someone say there is no ether. Well, they were lying to you. Because there is a quantum field, and the quantum field and ether are the same thing. Now, certainly, in the mid-1800s, physicists thought that ether acted more like a gas. So it had drag effects, friction, it had heating properties, and the quantum field doesn't have any of that. So the ancient ether certainly and fairly doesn't exist, but the modern ether, the quantum field, or zero-point field, as it's sometimes called, do exist. And how do we know that? We know that for a number of reasons. We know that, number one, space is polarizable. Electric fields exist. And space is magnetizable. Magnetic fields exist. And they are measurable. To start, we can think about what's the definition of ether. And I found one on thefreedictionary.com that's fairly good, representative. And it says, an all-pervading, infinitely elastic, massless medium formerly postulated as the medium of propagation of electromagnetic waves, or light. So, an all-pervading, that's a quantum field. Infinitely elastic, that's a quantum field in 19th century terms. We can quibble over what infinitely means in quantum terms. Massless, definitely, quantum field's massless, and it is a medium. And it says formerly postulated. Well, the quantum field is currently postulated as a medium of transmission and of light and other electromagnetic waves of varying frequency, not just visual light. So going back to this, when we talk about quantum field, and I'm a quantum field theorist, I've been studying quantum field theory for 30 years. My specialty is to consider properties of the related to the dipole model, that particles are supposed to be dipoles, where they have pairs of particles, with the prototypical pair being electron and positron, a matter and antimatter pair. So this pair can start out nothing, then go out over its wavelength, and collapse back to nothing and annihilate and disappear into space. And so these quantum fluctuations are happening all the time. Because we're looking at pairs that are matter and antimatter, they have opposite charge, plus and minus. So they're electrical charged dipoles. Well, these electrical charged dipoles can orient themselves to regular charges. So if I have electric charge here, say it's positive, and say if my thumb's positive and my finger's negative, the dipole will flip so that the negative is closer to the positive charge. And that will create electric fields. So space becomes polarizable and electric fields can exist, and it's part of quantum field theory. Similarly with magnetic fields, a dipole can rotate, and when a dipole rotates, it creates a miniature quantum magnet. And you can tell which way the North Pole is by curling your fingers of your right hand into the direction of rotation, and your thumb points to the North Pole. So a quantum rotating dipole creates a quantum magnet. And these quantum magnets align with quantum fields. And by that way, space becomes magnetizable. The quantum field becomes magnetizable because it's filled with quantum dipoles. So when a photon's moving through space, it has a rotating electric and magnetic field, and that field is rotating and magnetized quantum dipoles. And in addition to that, U.S. physicist Robert Dicke realized in the 50s, and probably others realized beforehand, that once you have a dipole medium in space, that the electric and magnetic constants fall out of that. That they become a natural phenomena that is related to the quantum field dipoles and their polarizability. And I'll get into that in more detail in other videos. But the speed of light is a function of permittivity and permeability. Now, in many cases, you may be taught in school that the speed of light is the most fundamental constant of all constants. That's not true. Permittivity and permeability are more fundamental because they're fundamental properties of the quantum field, and you calculate the speed of light as a secondary property. And in that way, ether, the quantum field, becomes the luminiferous ether, the medium of transmission of light. Not only do the electric and magnetic fields travel through the quantum field, but the speed of light is a quantum field property. In terms of ether drag, to the extent that light experiences a drag due to ether, it is the ether, or the quantum field, that gives light its speed. It determines the speed of light. So some of you may say, well, what about the Michelson-Morley experiment and ether drag? Well, ether drag is not a real thing, not in those terms. And people should know better. And I'll do another video on that as another one of the greatest lies in physics, that the Michelson-Morley experiment disproved ether. It just proved that physicists didn't know what they were talking about. There are other important proofs of the existence of ether, or of the quantum field, that I'll go over quickly. Number one here, or letter D here, is the Lamb shift. Willis Lamb, an American physicist, was measuring the spectrum of hydrogen. And in his measurements, he saw that there was a difference between the calculated values using quantum mechanics and the measured values that he got. And Hans Bethe, a German-American physicist, was able to realize that the reason for this difference was a quantum field interaction. So the Lamb shift was one of the first more in-the-weeds types of experiments that proved the existence of ether in the quantum field. Most people will say just the existence of electromagnetism and electromagnetic fields is proof of the existence of the quantum field. And I agree with that. So Willis Lamb and Hans Bethe both won Nobel Prizes. Another one is the electron self-energy, and then the G-factor. The G-factor is a factor related to the magnetic moment of the electron. And it's been calculated to very high accuracy, and it's considered one of the triumphs of quantum theory. Well, the G-factor correction term is based on electron self-energy, which is based on quantum field effects. So the electron correction factor is principally quantum field effects as they apply to the electron interacting with itself and its own magnetic field interacting with the quantum field. So the G-factor and electron self-energy, both of which are known to exist and both are known very accurately, are quantum field effects. Well, next time on the list is the Casimir effect, which I consider to be a real tour de force of physics, and that it's really important to the quantum field theory. In the Casimir effect, you have what are called van der Waals forces in space. These are forces that cause the space to jiggle and have a little bit of pressure. Basically, you have like two dipoles together. If the charges are the same, it causes the quantum fluctuations to contract a little bit. And if they're different, they expand a little bit. So this causes space to jiggle, which causes it to build up pressure. And so what Casimir realized, if you have two plates, that longer wavelengths, longer than the distance between the plates, won't exist in there. And that as you get closer and closer, you get fewer and fewer quantum fluctuations of the longer type. And when you get down to 1 micron or so, there's enough pressure that it pushes the plates together. Now, it took almost 50 years until the late 90s before someone experimentally showed that this is true. And they did it initially with a sphere and a plate because it's easier to control the distance. And actually, Casimir effects also occur between two spheres and lots of other different types of shapes. And there's even some shapes where you get a negative effect, where objects get pushed apart instead of pushed together. But this tells us that the Casimir effect tells us that not only is space filled with dipoles, which confirms the particle pair model, and also that they jiggle, which makes a force, and that force pushes on objects. And if there's differential in the force pushing on objects, it can cause objects to be pushed together or apart. And then, which is work. If you're accelerating an object, you're doing work. So the quantum field can do work by way of these van der Waals forces that occur because of the Casimir. The next is spontaneous emission. Spontaneous emission happens when an atom emits a photon. This is called spontaneous because initially you didn't know how it occurs, but now it's thought that the way spontaneous emission occurs is because it's triggered by an interaction with a quantum fluctuation, and that causes an electron to change its energy state, and then a photon gets emitted. So spontaneous emission by atoms is considered to be evidence of a quantum field. Next on the list is proton scattering. With the proton, our current understanding, which started with Richard Feynman's idea that there were small little particles he called partons, and thousands of them in order to explain the way protons scatter. So what he thought was the spherical structure of the charge radius of the proton had many, many partons in it. And nowadays, what we realize is those partons are quantum fluctuations. The quantum fluctuations form some kind of unidentified structure, at least unidentified in the standard model, of quantum fluctuations. And in the standard quark theory, they're considered to be quark and quark pairs and gluon pairs that form the quantum field within the proton charge radius. I'm working on ideas where it's any proton pairs, but that's a story for another day. But in any case, proton scattering also supports the idea that there's quantum fluctuations. Then we have blackbody radiation. Blackbody radiation in a vacuum occurs when a quantum fluctuation interacts with the body, gains some of its thermal energy, and then that thermal energy converts the quantum fluctuations to a photon. So if we have a vacuum chamber and we take all the air out, we can still have quantum fluctuations interacting with the chamber walls and gaining thermal energy from that, so that an empty vacuum chamber will have some generally microwave radiation inside of it because of blackbody radiation. We can also consider the cosmic microwave background radiation because that's a blackbody spectrum as has been measured, which indicates that it's coming from quantum fluctuation interacting with something that has thermal temperature that's in space. We don't need to get into details of that in this video. Another one that's interesting is dynamical Casimir effect. It's been experimentally proven to exist as well. The way it's generally described is you have a rotating mirror, a spinning mirror, and if it's spinning fast enough, it'll transfer kinetic energy to a quantum fluctuation before the quantum fluctuation annihilates. And because that quantum fluctuation has energy, it's converted into a photon. And this was proven in a somewhat different experimental apparatus in 2010. Then after that, we have Hawking radiation. And this one really bugs me because TV physicists and other talking head physicists love to talk about Hawking radiation. But some of those same physicists will say there is no ether, or they'll be opposed to the particle pair model of ether. But Hawking radiation is said to occur because you have a particle pair. One pair crosses the event horizon of a black hole, while the other one converts to a photon, and the photon escapes, taking away energy from the black hole. That's the basic idea. So anyone who supports Hawking radiation is supporting quantum field theory, and by extension, zero-point field theory and ether theory. Then you have Unruh radiation. Unruh radiation occurs when a body accelerates and it makes the quantum field produce radiation. And that radiation is related to blackbody radiation and the dynamical Casimir effect. It hasn't been measured, but most physicists are pretty happy with the theory and agree with it. Even though some of those physicists may turn around and say there is no ether. It's inconsistent. In addition to these, I've actually been working on understanding weak interactions as they relate to beta decay, particle decay, and such. And I think those are all quantum field interactions too, just much like spontaneous emission is. So any of those types of interactions are demonstrated evidence for the quantum field. So anyone who's a quantum field theory denier that says it's all bunk, they have a lot of work to cut out to them. They have to come up with alternative explanations for all these things on the list. I don't think anyone can do it. You have to have dipoles to have van der Waals forces. So that's top of my list. If someone's a quantum field theory denier, so explain van der Waals forces in your alternative theory. And so anyway, we have very strong evidence the quantum field exists. The quantum field is identical to the ether. It's identical to the 0 point energy. So all three are the same thing. And no one should be saying that there is no ether. It's a lie. Anyway, if you like my video, please like, share, subscribe. And if you want to learn more about the quantum field theory, you can watch more videos in the future, or you can read one of my books. I put some of the links below in the description. And also, I'm an independent researcher. I don't work for a university or anyone else currently, so if you want to support me, I have a Patreon account as well. Thank you very much.